Hi, my name is Daniel Craik. I'm a postdoc at MIT working on the LHCb experiment. I'm working on the Allen project to develop a GPU trigger for LHCb, which I'll talk to you about now. So LHCb specializes in the study of beauty and charm decays. Our current first level hardware trigger uses information only from our calorimeter and neon detectors, so there's no tracking information in there. But at run 3, we plan to run at 5 times higher luminosity than we're currently running. And at this point, charm and beauty decays are expected to occur in roughly a quarter of bunch crossings. This is a rate that we couldn't hope to write out. So we really need to be able to trigger effectively at this very high rate. So now we're not just searching for needles in a haystack, previously, but we're actually searching for needles in a stack of slightly less interesting needles. And that really needs as much information about the event as soon as possible. So one way to do that is to run tracking. If we want to run a trigger that is going to perform at very high rates, we want to do a lot of parallelization. And one way to get that is to run on GPUs. So if we look at the flow of what was happening in the trigger before, this is run 1 and run 2, and you notice we have this hardware trigger, which was significantly reducing the rate right at the start. We now no longer have this for run 3, so our first software trigger is going to have to perform at a 30 times higher rate with 5 times more stuff to process. So that really needs a lot of parallelization. Another benefit of running on GPUs is if we're on GPUs, then we no longer need to install these on this CPU farm, which we were previously piping everything to before running HLT1. We can install the GPUs on these event builder machines closer to the detector, and that reduces the data transfer rates needed. So this new trigger setup offers a significant efficiency improvement for many of our physics channels. Often up to 10 times. So what is the Allen project? So we implement HLT1 on GPUs. The project is named in honor of Francis E. Allen, a pioneer in parallelization. It is a generic configurable framework, so you can install another arbitrary sequence of GPU and CPU algorithms. However, we have configured it to run the HLT1 trigger. It's a standalone software package which you can find here and has very few required dependencies. There are additional dependencies that you can plug in to get more functionality. One of the features I'm going to highlight is the built-in validation and monitoring. So the overall strategy is instead of processing events one event at a time and attempting to just parallelize within events, we can send in thousands of events into our GPU at once, and we can parallelize not only within events, but across events. It's cross-platform compatible with CPU architectures, so if you don't have a GPU handy and you want to test it, you can compile it for CPU. We've demonstrated the technical feasibility, and it has now been adopted as the baseline technology for the first level trigger in run 3 of the LHCb detector. So the IRIS-HEP portion of the project, which I'm working on, is now shifting its focus from a more global scope to specifically work on the monitoring component, which is what I will talk to you about for the rest of the talk. So the Allen monitoring currently looks like this. We've got all of these streams running on our GPU device, processing events. Each of these is paired off with a thread on the host, which is handling any CPU algorithms within the algorithm stream, and also spooling in events. And then this all gets passed back to our main thread. Now, currently our monitoring runs in a separate thread over here, which means any information you want to construct histograms or counters from to monitor needs to be sent off to this monitoring thread. But this is much more intensive, both in terms of it's harder to balance a larger number of streams, but also if you want to monitor things which aren't written out into the output of the trigger, you're sending additional information to your monitoring that doesn't need to be sent. So the goal for run 3, we're working to incorporate this monitoring as part of the base class for our algorithms, so that each algorithm can define its own counters and histograms, and those can be populated within the algorithms themselves. That means for GPU algorithms, you don't even need to send the information away from the device. You can just send the histograms. For host algorithms, it only needs to go as far as the corresponding thread. So the goal is to have this new functionality in place in time for the start of run 3.